So we just wanted to look very quickly at two other versions of hypothesis tests that might be useful for us. We've got, notice, I've got a two sample test for a difference in means, right? So oftentimes we might worry about the average male wait time and the average female wait time, right? Or average male income, average female income, right? If we're thinking about different groups and we're comparing what their average is, we can not ask a single question about is this value greater or less than some number, but rather are these two averages, how do they compare to each other, right? So the way that we carry this out, right, notice that if we want there to be equality, or if we are investigating if there is not equality between these, we could do if the females are not equal to the average of the males, then what's got to be in the null hypothesis is that the females are equal to the males. And for the most part, these types of hypotheses tests get carried out the exact same way as the other ones, right? The test statistic is the only thing that's different. Hop it back one quick second is this test statistic. That's the only place that you do something different, is the way that you carry out the test statistic. What I want to point out here is we can do a little bit of algebra, and we can, if we bring this average male to the left-hand side, then what we have is that the average female minus the average male, that difference is equal to 0. These two things are algebraically correct, right? And so we can carry out the hypothesis test just like before, right? Whereas earlier we had a single average and we were asking whether it was equal to or not equal to some value. Now, all we're doing is just a linear combination of these averages and asking, is it that linear combination equal to or not equal to? But it's equivalent to asking whether those averages are equal to each other or not equal to each other. And so it's not much of a big difference, right? The other thing that we want to very briefly talk about is Anova. Right, and so in order to do the Anova, the analysis of variance, it's a very, very similar concept that we're going to come back to in regression, but all it's basically saying is this slight extension of what we just talked through, right? Instead of asking, are males and females equal to each other, this is asking, are all of the group averages equal to each other? And so, again, remember that your null and your alternative have to be complements of each other, right? So if in your null you have that each group has the same average outcome, the alternative is that at least one of those is different. You can have more than one, but the true alternative is that at least one of the means is different, right? And so we'll talk through a little bit later how to carry out some of the Anova in a slightly different context. What I did is I just pulled up where we started at this topic, the two different data sets, right? I've got 2018 call times, and I've got 2017 call times, right? And what we just said was that we can consider a difference in two means, right? We can ask the question, are the average call times in 2017 equal to the average call times in 2018. Okay, so this is the full write-up of the null and the alternative hypothesis. Again, the motivator for this was we've got this new training, and did the training do anything to the average time, the average call time, right? So we're really asking the question, right? Are the average call times different, or are they the same, right? We're going to assume that the new training didn't do anything until the data convinces us that it did cause a change in the average time, right? So that's why that's what we're putting in our null hypothesis, and our alternative, the burden of proof that we're putting the data on, is to convince us that they're not the same, right? And so equivalently, right, I can write the set of hypotheses either of these ways, right? It really is just this linear combination. Notice, does it matter which one I put first, 2017, 2018? It doesn't, right? I want to jump over to Excel because I want to talk about how we'd actually carry this out in Excel, right? So I've got I've got in column B, notice that if I go all the way down to the bottom of column B, then I'm going way down in my data set. I've got, oh, sorry, column B is my 2018, and so I'm only going 40 observations deep in column B for 2018. Column E has, I just pulled over the data into from the other data set so that they were both in the same worksheet, right? It's got many more observations. So how do I carry out a hypothesis test? Under my data tab, data analysis allows me to do, I'm going to make this big. Under my data tab, this data analysis brings up a number of different things that we would want to do. And we've got a couple of Z, right? So we've got a Z test on 2 sample means, and we also have a T test. Do you recall what's the difference between a Z test and a T test, right? Z test should be used when we know what the population standard deviations are. We don't necessarily know those for these call times, right? So we're probably going to want to use a T, but notice there are 3 different options for a T test, right? Paired 2 sample for means, 2 sample assuming equal variance, 2 sample assuming unequal variance. So when do we use which, right? So this T test for the paired 2 samples, right? You'd want to use that if you know that you've got the same person for your first and your second set of observations, right? So this is pretty classic whenever you do like a pre-test, post-test, right? So at the beginning of a class, you take a test to see how much you remember about statistics. And then at the end of this test, end of the semester, you take a test again. And if you're doing a pre and a post test and it's the same test and the same number of individuals taking it, then we could refer to that as a paired sample, right? That's not what we have here, right? We've just got a bunch of different call times, right? But they were not the same callers, and so this isn't a paired sample. We're going to want to use one of the other 2s. But the question is, what's the difference, right? So we've got 2 samples, but notice they assume different things about the variance, right? So we've got the variance in B and we've got the variance in E, but should we think that those sets of call times have the same variance, or should we assume that they have unequal variance, right? For the most part, you're going to want to go with the assumption of unequal variance unless you can be convinced otherwise, right? So let's go ahead and select that one initially. And if we click OK, it brings up a little dialog box, right? And so this is pretty straightforward, right? We have to input 2 different ranges of information, right, that correspond to our 2 different categories of things, right? Our first range, let's have that be my 2018 call times. And so that's in this construction of where I put the data together, B2 through B41, right? And then for range 2, that's going to be my call times from 2017. So let's go ahead and do E2 through, oh boy, it goes all the way through E1000, right? So we've got a much different number of observations. Here we go. What do you think we put in this hypothesized mean difference, right? If you recall, we were assuming that their difference was 0. We were asking, are they different from each other? Notice that Excel's got some flexibility into it, so you don't have to necessarily assume that they're equal to each other. You could assume that there's some kind of difference and carry it out in this, right? I forget, did we include labels? I'm going to have to go back and look at this. No, we started in B2, and so we don't have the labels. We get to enter what our level of alpha is, the level of significance, the level of committing a type 1 error, and we also get to choose what the output range is, right? So let's go ahead and put this stuff, oh shoot, I accidentally adjusted that, right? So I need to, you always got to be careful when you're doing these dialog boxes to make sure that you highlight the right thing. So I needed to highlight in that output, and then I could go up to, what was it, I think G3 is where I wanted to put it. Go ahead and click OK, and notice, right, what all is it telling me, right? So it's a little bit messy, but hopefully based on everything else that you have, that you've listened to about the way that we've done hypothesis testing, you can work through what this information is telling you, right? So you've got 2 different data sets, right? You've got the first one, so those results that Excel just gave me highlighted that I had screwed something up, right? Because I have 2 different data sources, and the first one is 142. That's not right. I had clicked the labels, but if I click labels, then I got to make sure that the data that I'm inputting in the range includes that label, and I hadn't, right? And instead, what it did is it took that first observation and used that as a label, and so some of these calculations were going to be a little bit off. Glance through these numbers real quick, and then we've readjusted everything. We're going to overwrite this, but notice it's going to be a small change, especially over here. It's going to be a very, very small change, right? Go ahead and overwrite it, and notice, yeah, these numbers aren't very much different, right? But they are. We've got a little bit better. I forgot that it was not labeling the year. So the first one is the 2018, and the second one is 2017. So what do we've got? The first line tells me the average of these call times between the 2 years. And again, the data looks like call times went down a little bit, right? It automatically estimates the variance. Those variances aren't that much different from each other, right? So we made the assumption that, or we calculated these things based on an unequal variance. We've got the number of observations, and we have the hypothesized mean difference, and we've got our degrees of freedom, right? And so this also gives me a t-statistic. Again, think about conceptually, where would this value of a t-statistic be? If you think about a t-distribution, which is the way that a difference in means would be, if we've got a t-statistic that's negative 1.92, where would that be? It's going to be to the left. It's going to be pretty far to the left, but how far to the left? This also brings up some information about that, right? So notice this gives you a fair amount of flexibility. So were we doing a one-tailed test or a two-tailed test, right? We were carrying out a two-tailed test, asking, are they different from each other? And in that case, the critical t-value would have been 2.01, and the p-value associated with that is 0.06. Notice, with our level of significance of 0.05, if we were just asking if the training did anything, right? We're not rejecting our null hypothesis, right? But if we're asking, if we're asking a one-tailed test, saying did the training reduce times, then it looks like our p-value is a little bit smaller, right? We were using a different critical value, and we have a different p-value associated with, but in general, right? So that's how we carry out this sort of hypothesis testing in Excel.